All right, so let's go ahead and take a look at the second question here. So for parts of the free response, okay. All right, so here's the reaction. So we have magnesium plus hydrochloric acid going to magnesium chloride and hydrogen gas. An experiment, a student places small pieces of magnesium into a beaker containing 250 milliliters of 6.44 molar hydrochloric acid. A reaction occurs represented by the equation above. Right, the balanced net ionic equation for the reaction. Okay, net ionic equations show us what actual atoms or ions are participating in the reaction. Okay, so when I want to see a net ionic equation, what I'm going to look for is what's the actual reaction that's going on, or what's changing states. Okay, so I'm going to rewrite this over here and give me a little bit more room. Okay, so we have magnesium solid plus 2 hydrochloric acid aqueous going to magnesium chloride aqueous plus hydrogen gas. Okay, so this is kind of a review from last year. If we think of what aqueous means these split apart, right? So if I wanted to write the complete ionic equation, I'm going to go ahead and do this. So magnesium solid plus 2 H pluses. Why? Because I have 2 hydrogen ions from hydrochloric acid plus 2 chloride ions from hydrochloric acid, right? Aqueous means, hey, this is actually how that represents. Goes to, again, aqueous over here, so magnesium. It's going to have a 2 plus aqueous plus, again, I've got 2 chloride ions aqueous. Again, because the aqueous tells me what about this? You know, you've got those positive and negative charges in your ionic compound, and they've been split apart by water. Plus H2 gas. Okay, so for a net ionic equation, we want to see what is actually changing. Why do we actually see a chemical reaction? So let's look. What changes? I go from magnesium solid to a magnesium 2 plus ion. Well, that's changed. Magnesium has lost 2 electrons in this case, so that's going to be in my net ionic. So Mg solid, okay, plus, let's see what else happens. I go from 2 hydrogen ions now to, hey, elemental hydrogen in its gaseous form, okay? That's going to be my net ionic equation because it changed. It went from a +1 ion, a cation, to its elemental state. 2 chloride anions aqueous, 2 chloride anions aqueous. Those did not change. They are the same here and here. So they do not appear in my net ionic equation. So then what we see is magnesium 2 plus aqueous plus H2 gas. That would be your net ionic equation for that. That's a review. That's not really kinetics, but net ionics, just what do they show me? What is actually changing. Chloride did not change, therefore it is not in my chemical reaction. All right, let's go on here and see what else we got. A student collects H2 produced by the reaction and measures its volume over water at 298 Kelvin. After carefully equalizing the water volumes inside and outside, we'll talk about why would they do this. What's the point of doing this? Oh, that's not very good straight line there. Sorry. Try that again. After it equalized, this is an important statement. As shown in the diagram below, the volume is measured to be, okay, so I'm getting a volume measurement, 45.6 milliliters, okay? Oh, and then I'm getting some pressure measurements here. I've got outside pressure is equal to 765 torr. And then it says, hey, the vapor pressure due to water, so this is pressure, and I'm going to put H2O, is 24 torr. Okay. So let's come down and kind of look at the drawing they've got here. All right, what is important about this water line being equal? Okay, so first off, there are gas particles outside here that are hitting this constantly and bombarding it. Okay, that creates gas pressure. And what do we know? Well, we know from our problem that it has a pressure of 765 torr. What we also know is we're collecting a gas inside the tube. So we've got gas particles hitting here as well, pushing this water back down. Okay, and also bouncing off and hitting away and all kinds of stuff. But if our levels are equal, What's that tell me about the pressure that this is putting on and the pressure inside the tube here? If the levels are equal to each other, that tells me that the pressures are equal to each other. So the 765 torr of the atmospheric pressure of these guys is equal to the pressure of the particles inside of here. Why? The water level is the same, so we know we're pushing down with the same amount of force. So this gives me the pressure inside this tube. Okay? So the atmospheric pressure is equal to the internal pressure when the water levels are equal. One other thing it tells me, though, it also says, hey, the pressure of the H2O, the water vapor, is equal to 24 torr. So let's think of what that tells me. Well, what I have here is I have some H2O molecules that are coming out of here, and now they're gas form, and they're creating a pressure too. So they're adding to that pressure inside of here. Some of that pressure, if we look back at our reaction, some of that pressure, is due to the H2 gas, and now some of that pressure is due to the water particles. Well, if 24 torr of it's due to water, and my total pressure is 765, I can find out 765 is equal to 24 torr plus the pressure due to H2. And we find out the pressure due to H2 then would be equal to 741 torr. So I take away the vapor pressure of the water, all right? So that's the pressure due to H2 in the tube right there. The number of moles of H2 produced. Okay, so I want moles, I'm talking with gas. I'm going to use PV equals nRT. And I know my pressure due to is 741 torr. Okay, my volume was what, 40, what did it tell me? 45.6 milliliters. You convert that to liters, is equal to N moles. Now my R here, I'm going to use a different R. Because if we notice right now, my pressure is in torr. Let me find my formula sheet. Here it is. My pressure is in torr, so I can't use the 0.08206. But if you look on your equation sheet, you have another R value that has torr in it. It's 62.36 liters times torr per mole Kelvin. Okay, so there's my R. And then my temperature was, what was it, 298 Kelvin. And now I just, oh, sorry about that. Make you guys car sick by doing that. Okay, and now I'm just going to solve for N. Okay, anytime you have a gas and you want to find moles, you're going to want to use the ideal gas law. The other thing you could have done and not use the different R value is you could have converted your pressure from torr to ATM. And that conversion is also on your formula sheet. There's 760 torr in 1 ATM. And what I got was the moles is equal to 0.0018 moles, or 1.8 times 10 to the negative third moles of H2. All right, so there's my answer for that guy. So that's gas laws and some review from last year, and I think now is where we get to the kinetics portion of this question. In a different experiment, a student places a piece of barium in the container, observes the rate of the appearance of H2 bubbles when barium added is much faster than the rate of appearance with magnesium. The student claims that the greater reaction is due to the difference in ionization energy between barium and magnesium. Explain the ionization energy difference, okay, in terms of atomic structure. This is electron configuration. So if we go back to last year, we think of our valence electrons for magnesium. Magnesium is in the third energy level, so its last two electrons are 3s2. Barium, on the other hand, is in the sixth energy level, and its last electrons are 6s2. Okay? The energy level, or where they're at on the periodic table, tells me on average the distance from the nucleus. So, on average, electrons in the 6s orbitals are much further away than the 3s orbitals. Okay, so 6 is greater than 3. It's on a higher energy level. So since these are much further away from the nucleus, barium's nucleus has much less control over them. Right? So it has a lower ionization energy, or it takes less energy to steal these electrons than it does to steal these electrons. So therefore, we should see a faster rate. Hydrochloric acid can be produced by the exothermic reaction between hydrogen and ICl, as proposed. A proposed mechanism for the reaction is shown below. So it's a two-step mechanism with a slow first step. Write the rate law for the overall reaction considered with the proposed mechanism. All right, so the slow step, or this can also be called the rate determining step. So this is the step that we want to hone in on, the rate determining step. So what we want to say is the rate is equal to K times the concentration of H2 times the concentration of ICl. There's my rate law. How do I know that? I look at my coefficients here. Okay? 1 and 1. All right? So it's first order with respect to both hydrogen and ICl. How do I know that? I know that from the slow step. An incomplete reaction energy diagram is shown below. Draw a curve that shows the following details: the relative activation energy of the two elementary steps and the enthalpy change for the overall reaction. Okay, enthalpy change. I must have missed something up here. Let's see if it says if it's endothermic. Oh, hey, it tells me it's exothermic. So this is delta H is less than 0 or negative. All right, I want to draw the energy diagram. It's got 2 steps. First step is slow. Second step is fast. All right, so I'm going to have 2 peaks here. The first peak is going to be higher. The second peak is going to be lower. It's an exothermic reaction. I get that. And then my products overall were 2HCl plus I2. And that's what your reaction curve should look like. Okay, so that's the rest of that one. This one had a little bit of extra stuff on there that wasn't kinetics, but hopefully after going over that, reviewing there, that helps you. Make sure we can write rate laws from slow steps. We can draw diagrams from mechanisms and slow steps, and that should be it. Have a great day, guys. Hopefully these 2 videos were helpful.